Hello and welcome to your first video about gas laws. We're going to start our discussion with by talking about kinetic molecular theory, or KMT. And kinetic molecular theory is based on 5 assumptions. And we're going to go through these assumptions one by one, and then we're going to talk about how these translate into the properties of gases. So the first assumption of KMT is that gases consist of large numbers of tiny particles that are far apart relative to their size. This means that most of the volume of a gas is occupied by empty space. So here I have a little simulation that I'd like to run, and this will help us kind of talk about what's going on with a gas. So the first thing I'm going to do is I'm going to pump the handle and get some gas particles going in this little box. Okay, so even though these gas particles are significantly larger than they should be, and I think what I'm going to do is I'm going to limit this to about 20 just so we can talk about what's going on. Okay, so there you see lots of empty space in between the gas particles. Collisions between gas particles and between particles in container walls are elastic. Okay, now elastic means that there is no net loss of kinetic energy. So if a particle bounces off the wall, it's moving as fast before it hits the wall as it was after. Okay? So no net loss of kinetic energy. Same thing happens with balls bouncing off each other. The third, gas particles are in continuous, rapid, random motion and therefore have kinetic energy. Now this is going to be really important. Kinetic energy is the energy of movement. So we're going to talk more about that in a little bit, but you can see the gas particles moving in a straight line, bouncing off each other, changing direction, but they're always moving, and yeah. There are no forces of attraction between gas particles. All right? If they were attracted to each other, like say if this ball here were attracted to one of the balls that it was going to hit, it would tend to stick together, and therefore you wouldn't have elastic collisions. The temperature of the gas depends on the average kinetic energy of the particles of the gas. So another way of saying this is that the temperature depends on the speed of the particles. Okay, so if I change this temperature, if I add heat and I make things a little hotter, okay, the particles are all going to move faster. Now this is going to be really important, so I want you to keep this in mind. All right, so let's talk about some properties of gases. Okay, the first one, particles of a gas expand to fill a container. Okay, now you saw this again if I reset this and I just push some gas molecules out. Maybe I'll need a little bit more. Oh, reset, push, push. Oh, play. Ah, there we go. Okay, messed it up. Okay. One more time, just a couple particles out. There you go. They expand to fill their container that they're in. They try to get as far apart as possible. Okay? The next one is gases are a fluid. Now, when I say fluid, you're used to thinking of things like water. Okay? Fluid just means that the particles flow past each other. And this again comes from the fact that they're not attracted to each other. Now, because the particles are so far apart, gases have a very small density. Okay? So, in fact, when we measured density at the beginning of the year of things like solids, we were in grams per milliliter. And now we're going to go up to grams per liter. Okay? So, we're 1,000-fold change when we're talking about solids versus gases. Okay? Because there's so much empty space, I can compress gases. Okay? I can compress gases. So gases, we say, are compressible. Now, the last two that the textbook talks about are diffusion and effusion. Okay, these are a little bit less important for us, but I want you to have an idea of what these two terms mean. So diffusion is just that gas particles will mix. Okay? If I add some light species, okay, you can see that they're pretty well mixed with the heavier species. They're the little red balls that are moving around like crazy things. Okay? And effusion is that gas particles will move through a tiny hole or pass through a tiny hole. Okay, so if I go back to if I open up this hole here, so there's just a little hole, you'll see gas particles, if my computer doesn't crash first, gas particles start to leave the container that they're in. Okay, so this would be an example of effusion, and they'll keep doing that until they're all gone. Okay? All right, so that's properties of gases. Now, one more term that I want you to know is I want you to know the term ideal gas. Okay, ideal gas follows the 5 assumptions of KMT. Okay, now most gases don't behave like ideal gases. We will treat them like they do, and usually it ends up being an okay assumption to make. But no gases are going to be truly ideal. All right, real gases do not behave according to KMT. So the worst offenders are polar compounds. Okay, think of things like NH3 or sulfur dioxide, things like that. Okay, non-polar gases are going to tend to be more real. So let's say things like nitrogen and oxygen. Okay? So ideal gases are kind of what everything are built on, and we describe gas behavior as if all gases were ideal. Okay? So let's get back to this idea that gases, the temperature of a gases is related to the kinetic energy of the gases. Okay? If we go back to our simulation here, and let's reset, okay, and I just add, let's say I add about 50 gases. Okay, now you can see that not all gases, not all the gas molecules are going at the same speed. Some are going slower, some are going faster, okay? So if I were to make a graph of the number of particles over here versus the kinetic energy over here, okay, where kinetic energy I'm basically going to call speed, okay? The equation for kinetic energy equals 1/2 mv squared, okay, where m is mass of the gas and v is velocity, okay, or speed. So if you have a sample of the same gas particles, the mass isn't going to change, but the speed might. Okay, so if I go back and I look at this and I say, okay, so some particles are going to be going slower, some particles are going to be going faster, what you'll see is that this has a bell-shaped distribution. Okay, and the average, this would be about the average, right? Okay, is going to be related to the temperature. Okay, so here's a, let's say a gas at some temperature. Okay, if I increase the temperature of the gas, I'm going to increase the average. So this is a gas at a higher temperature. We are going to use this graph a lot. So make sure that you know it, you love it, and you use it. Okay? Rock on. The next thing that we're going to talk about with gases is pressure. Okay? Pressure is defined as the force exerted divided by the area that the force is exerted. Now, I blatantly ripped this figure off from your textbook because I think it's actually really interesting. All right, so here, the force that's exerted on this ballerina, that this ballerina is exerting on the floor, is the force of gravity, so her weight. Now, if she's standing flat-footed, this area of contact is a little bit bigger. So if you take her 500 newtons of force, which corresponds with her weight, and you divide it by this 325 centimeters squared, you get this 1.5 newtons per centimeter squared. But if she goes up on her tippy toes, the area of contact decreases drastically, and you'll see that the pressure increases a lot. Okay? Now, again, if she goes up on just one tippy toe, her area halves and the pressure doubles. Okay? So, the question is, how do gas particles exert forces on their containers? Okay? So, gases exert force by colliding with the walls of their containers. Okay? So if I hit my hand against the wall, I can tell that I've exerted a force on the wall. I can feel my hand pushing against the wall, and I can feel the wall pushing against my hand. Okay? So gas particles are going to do something very similar. All right? So here's my gas container, and here's one gas particle, okay? And it's going to be going in a straight line, and it's going to run into the wall. And when it runs into the wall, it exerts a small amount of force on the wall, and then the wall exerts the same amount of force back, okay, and sends the gas particle in a different direction. Okay, it would, the way I drew it, it would technically go straight back where it came from, but for simplifying the drawing, I made it go off in a different direction. All right, so you can see, if I go back to the simulation here, okay, here's a pressure gauge, and here's the little pressure gauge sensor. So every time that a particle hits the pressure gauge sensor, the pressure of the whole system goes up a little bit. All right? And so if I increase the number of particles, okay, there are going to be more collisions with the wall. All right? All right, units of pressure. So the standard unit, the SI unit of pressure is the Pascal, and it's kind of a mess. All right, you'll notice that it is a derived unit. It's derived from the SI unit of force, which is the Newton, and the SI unit of area, which is meter squared. So it's 1 Newton per meter square, which we call a Pascal. Okay. Another one that we'll use a lot is a millimeter of mercury, or mmHg. So pressure that supports a 1 millimeter mercury column and a barometer. Okay, we're going to talk. You're going to look at how the pressure of the atmosphere is measured in a barometer, and one of the ways that was used was with a pool of mercury. Okay. Another one is a torr. It's short for Torricelli. Okay, it's another unit of pressure. And the interesting thing here is that 1 torr equals 1 millimeter mercury. Okay. The one that we use a lot in everyday life is an atmosphere. Okay, and the symbol for that is ATM. It's the average atmospheric pressure at sea level in 0 degrees Celsius. Okay. So here I have a box full of interesting things. I know that 1 atmosphere equals 760 millimeters mercury, and since 1 millimeter mercury equals 1 torr, 1 atmosphere also equals 760 torr. 1 atmosphere equals 1.01325 times 10 to the 5th pascals, or 101.325 kilopascals. Now, if you're paying attention at all, you'll notice that this is all set up to be conversion factors. Yay! So you will, oh boy, you will be converting between units of pressure. Okay? Tire gauges use pounds per square inch, but it's kind of a ridiculous thing that we won't use ever. All right, you will see bandied about the phrase standard temperature and pressure. And you're going to need to memorize what this means. Oh no, memorization. Oh no. Okay. Standard temperature is 0 degrees Celsius. Ouch. And standard pressure is 1 atmosphere. Oh no, this is so hard. Okay, so standard temperature, 0 degrees Celsius, pressure, 1 atmosphere. We call this, standard temperature and pressure, we call this STP, which you will see a lot in problems. Okay? Onward. Here we go. As promised, a conversion factor. A conversion problem using pressure. Convert a pressure of 1.75 atmospheres to kPa and to millimeters mercury. Now you'll notice that there are actually 2 conversion factors being asked here. Okay? Now, as always, I'm going to start up my dimensional analysis the same way that I always do. So let's do kPa first. All right? So, question mark, the unit that I'm looking for, kPa. My given, 1.75 ATM. Now, I'm still not thinking. I write my atmospheres down here. Now, I know that if I go back to the table, that I can convert between atmospheres and kPa. So I can do this in one step. Okay, my atmospheres are going to go away, and I can fill in the values. 1 atmosphere is 101.325 kPa. Okay, and if I do my calculations, and keep in mind I'm working with 3 sig figs here, I get 1.77 times 10 to the second kPa. Okay, I can do the same thing with millimeters of mercury. 1.75 atmospheres. Okay, put my atmospheres on the bottom. I can do millimeters of mercury on the top because I know that one from the table. There's 760 millimeters mercury in 1 atmosphere, and I get 1.33 times 10 to the third millimeters mercury. Okay? So that's it. That's converting pressure. All right. Now, the next thing that we're going to talk about is Dalton's Law of partial pressures. Okay, Dalton's Law of partial pressures. Super, super easy. It just says the total pressure in a container is equal to the sum of the pressure of the first gas plus the pressure of the second gas, plus the pressure of the third gas, dot, 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 as far as you want to go, okay? Now, this makes sense. Let's go back to our simulation here. Okay, I'm going to go back to 10 particles of the heavy gas. Okay, here are my 10 particles of my heavy gas. Okay, now this gas is exerting a pressure on the container by colliding with the walls. Okay, if I add another gas, it has no effect on the collisions of the blue gas. The red gas has no effect on the collisions of the blue gas. The blue gas has no effect on the collisions of the red gas. Okay? However, the red gas is now colliding with the wall as well. So you're going to get the extra collisions, so the total pressure is going to increase. Okay? And if I isolated them, the pressure of the red gases would be one thing. The pressure of the blue gas would be another thing. And if I add them together back in to this diagram, that would be the total pressure. Okay? So that should make sense. Now where this is going to get a little tricky is a special case. Okay? Oftentimes in chemistry, you isolate a gas by collecting it over water. Okay? So here's an example. There's a little bit of metal down here, and this is actually hydrochloric acid and magnesium. Okay, and there's a reaction happening, and hydrogen gas is being produced. And as the hydrogen gas is produced, it goes through this bubbler here and is collected at the top of this container. Now, what that means is that what's at the top of this container is not just pure hydrogen gas. There are also some water vapor molecules. Okay, so P total would be the P of the gas, which in this case is H2, plus the pressure, the partial pressure of the water vapor. Okay, now it's tough to tell from this diagram, but this water, the water in this tub here, is actually open to the air, which means that the pressure up in here is going to be equal to the pressure that's pushing down out here, okay? Which means that the pressure inside, the total pressure, is going to be the atmospheric pressure. So we have P atmosphere equals P gas plus P H2O. Okay, so this value is going to be temperature dependent, and it's found in the textbook. It's table B8, B as in boy, B8, and it's on page R63, and this is in the back of the textbook, okay? So Yours is going to look a lot like this, but yours is going to be blue, or sorry, it's going to be green, and it's going to say B8. Okay, it looks a lot like this. So notice that this water vapor pressure is given in terms of millimeters mercury, or kPa, which means that you're going to have to be careful about what unit you're using. Okay? So, how is this used in a problem? Student has stored 100 milliliters of neon gas over water on a day when the temperature is 27 degrees Celsius. If the barometer in the room reads 743.3 millimeters mercury, what is the pressure of the neon gas in its container? So, the barometer measures the atmospheric pressure. Okay? So, I'm going to use PATM equals P gas, which in this case, I guess I can take out, well, here, I'll do that later. P gas plus PH2O. Okay? Now, as it turns out, this 100 milliliters, not important information. Okay? I am going to need the temperature of the gas. Okay? Because this temperature tells me what the partial pressure of water vapor is going to be. Okay? I also need to know the pressure in the room reads 743.3 millimeters mercury. Okay? Because that's the atmospheric pressure. And I'm going to use the table to find this, which means that I can solve for the pressure of the neon by subtracting H2O, PATM minus PH2O. Okay, all I did here was subtract H2O from both sides and then swap them. Okay, atmospheric pressure is 743.3 millimeters mercury. Okay, and I'm going to subtract the pressure, the partial pressure of water. And so if I go back and I look at the table, I want to make sure that I use the correct units, which is in millimeters mercury. Okay, I'm at 27.0 degrees Celsius. So I find 27 degrees. I find millimeters mercury. There it is, 26.7. Okay, so I do my little subtraction. Okay, and I get 716.6 millimeters mercury. Okay. This has been a lovely introduction to gas laws. I hope you have found it illuminating. I'll see you again when we talk about gas laws.